I'm about to begin discussing chapter 7 of your book, that's a 7, which is about kind of two things. One is problem solving, and its broadest sense, and the other is about algorithms. And the reason I say that those are two different things has to do with the way that they're presented in the book. As far as problem solving, we're going to be talking about a process of heuristics, which is a fancy word for what I would best describe as guessing with strategies. So intelligently, in order to come up with a solution and checking it. And also we're going to be kind of talking about a process for solving problems from a 1945 book by POLYA. And I don't know if his name has any funny symbols above. Let me check real quick. You gotta respect people by spelling the name correctly. I don't see it. So I'm going to present today mostly this. And chapter 7 of your book, that's supposed to be a 7, also goes into a great amount of detail of algorithms, where what it is really talking about is a bit of pseudocode conventions, and it's going to talk about control structures, which is a fancy way of saying things like if, then, else. So it's how we specify whether we're going to do a block of code or a set of instructions under different conditions, as well as looping. You can say while this is true, do that. You can say repeat this many times. You can say for each I in the range 1 through 10. So these kind of looping constructs. And also with respect to this, we're going to talk about a little bit about data and composite data. We're going to talk about records. Come on. We're going to talk about arrays. And it's actually quite a bit. So this I'm going to split off and discuss in probably a separate video. Today I want to focus on problem solving. So the first, again, for the first thing that I want to bring up is the book was, I think, How to Solve It. Written by POLYA in 1945. So the book is a book written for mathematicians, and actually specifically for teachers, really was what the focus was, for teaching math to people. And the focus on how to prove it, how to generate proofs in some ways. But however, the idea can easily be you can just replace programs, and everything works almost exactly the same, right? The title, there's like a subtitle, a new aspect of the mathematical methods. This is from 1945, so 1945, but it's still very relevant. So often you'll be, for example, in CS interviews, right? In computing interviews. you'll be asked a question, and it'll be a question that they don't expect you to know the answer to. And so what people who ask you questions, there'll be riddles. People will ask you interview questions like, oh geez, so you're in a building and it's got 4 windows and all 4 windows face south. A bear walks by. What color is it? And that sounds completely silly and maybe irrelevant, and you think, what does that have to do with computing? And what they're really trying to get at is a process. What process do you go through in order to determine, say, what color the bear is? So what is the process that you use to solve problems? So is right or wrong in a computing interview is less important than the process that you would use to come up with a solution. And people ask you these kinds of questions, for instance, in interviews, because they want to know more than if you can write in, say, maybe HTML or C++ or Python. There's all of these different tools that somebody might want you to know. And if you're interviewing with like a small startup or somebody who they just needs this specific skill, they might focus on that. But what people tend to find when they're looking for employees to hire is what's really important is, do they just have a general purpose process? So can they do problem solving? And that is the most frustrating thing, is when people don't seem to have in mind a process for solving. So I could ask you to do something like find the tallest person in a room, or if I have a bunch of products, I could say find the most expensive product in this list. And if you can't realize that both of those are the same problem, here's a set of numbers, find the maximum in the number, you're not going to be a very useful problem solver. So there's just a general process and principles for solving problems, and this book really enumerates them. And what it does is it breaks the problem solving process into kind of 4, they call them steps, but let's just say phases of problem solving. And the first one is understanding. And there is a convenient reference in your book, and if you go online you can find all kinds of great PDFs for this, that take these 4 phases and drill down on them. But the first thing that you need to do when solving a problem is something that people often don't do a very good job of, which is actually understanding what is the problem, right? So what is it that, what do you know? What's known that you could take advantage of? What's unknown? You know, so you have to set the scope. And what's the input, or what's the data involved? And most important probably is he puts the condition, and I'll word it or like this criteria. How can you tell that it's solved successfully? How can you tell whether you've actually solved the problem? So there's a really important, some people would call this process, but I call it an aspect of understanding, which is huge. At this point in time in solving a problem, you really want to be drawing a picture, right? So you have 4 walls. Each wall has a window, so you come up with some representation for a window, and all 4 windows point south. And right off the bat, you've got to ask yourself, can I do that? Can I have a room with all 4 walls facing the same direction? And clearly that configuration isn't going to work. So if all 4 windows point south, maybe I'm going to figure out that if I'm on a globe, that could work if because south always points away from this North Pole. So maybe that means that my house is up here at the North Pole. And having a picture and being able to quickly draw a picture is an important tool in understanding the problem, right? Another thing that is part of this, which is establish a notation. So going with pictures, imagine you've got something like, oh, there's a triangle, and it's got a side of length A and a side of length B. I've got a fourth side, which we'll call the hypotenuse, and I want to know what is the length of the hypotenuse. You know, so you establish a notation, and part of what your notation might include is things like the labels or the numbers that you're going to use to indicate maybe the sides of the triangle. And from here, if you have been paying attention in math, you know that the hypotenuse is going to be the square root of a squared plus b squared. And there are, you know, wonderful ways to represent that by pictures, and you can prove it, etc., using pictures as well. But at least drawing this picture first and establishing the notation is an important very first step that you should always be thinking about when you're trying to understand the problem. This happens way before coding, way before coding. However, it is a process that you'll return to multiple times, because you'll try to understand a problem, you'll draw a picture, etc., and you'll move on to the second step of the process, which is kind of coming up with a plan on how you might go about solving it. And in the process of coming up with the plan, you realize, oh yeah, I didn't think about this detail. And you'll come back up to this step and try to think about how you could understand the problem better again. So continuing along with phase 2 of this process. So 1 was understanding, or understand it, and 2 is develop a plan. And this is really where POLYA puts the most detail. Although I would say that this is probably more important, right? And what he has is a bunch of strategies that you could use to try to find a plan. And of those strategies, I'm going to highlight a few key ones. I guess the number 1 is look for familiar things. And I'm going to underline the word familiar things. So what makes you an expert, or what makes you good at solving problems, to a large part is recognizing that you've solved a problem which in some way is going to be useful to solve a new problem. And then you have to take that useful thing and somehow transfer it over to a new domain, right? And that can be hard to do. So you're going to look for familiar things and think about it. Have you seen it before exactly, or in a slightly different form? Maybe somehow slightly different. And if you can recognize that, then maybe there's something that you could bring over. Look for related problems. Look for problems that have similar unknowns or similar known facts, similar criteria. Look for a problem that yours would solve. in addition to the one that you originally have? So is there another problem that yours could solve? And if that one's already been solved, you could work backwards, right? Look for, here's a big one. Is my problem I can break mine into parts. Break it into parts. Usually smaller parts. And can I solve the small parts? Right? This is divide. There's a big algorithm development strategy. And conquer. If I can break my original problem into smaller parts, and then I can, maybe those parts are easy to solve. So you divide it into smaller parts, and then you solve those smaller parts, and then you somehow combine those solutions, and now you've conquered your original problem. There's ways that you can say, how about what if I kind of relax the criteria? Okay, what if I don't need this to be true? You know, what if I add data or add information? Right? And it doesn't sound like that's useful, but you can solve that problem, and then that might give you insight into the original. You're looking for insight into the original problem. Or you might just change your understanding of what the problem was to begin with, right? Maybe the first one might not even be solvable, and you can discover that doing this. There's some big ones. So I've got here, I'll circle in red, divide and conquer. That's a huge one. There's another thing I'm going to throw in here, which is guess and check. And a related idea of continuous manipulation. And this guy here is kind of like your brute force approach, which isn't likely to work for interesting problems, but you can still learn from it. And it's generally the first thing that I want to try. So the way to think about this is, you know, like if you've ever seen the tangrams, you've got squares and circles and triangles, and you're supposed to make some weird shape. Often what I tend to do is I'll just take this guy and I'll keep rotating him and trying every possible place that I could fit him in here until I find a spot that he fits. And then I say, okay, that's good, and I'll do it with the second one, and I will just keep manipulating it until I find a solution, and then I'm like, yeah, I did it. And that works for a bunch of puzzles. Like there's those little, like there's a ring, and then there's like these little pieces connected, and you need to get the piece off of it. You know, you just keep twisting those little metal pieces until you get them separated. That's probably a horrible picture. I'll try to find a picture of one of those ring puzzles and put it in there, but I think hopefully you know what I mean. Similar guess and check. I mean, you can think about if you've got a puzzle, right? So you have some other piece, and you can't quite tell if it's going to fit, but you think it might. So you go over there, you put it in, and you find, oh, well, that one fits, but then that piece doesn't fit, so I can rule that out. So you guess at a solution, you try it, you check it, and find that it doesn't work. Right. So, for instance, I could, if I didn't know what the hypotenuse was, right, I could see that it's longer than A and it's longer than B, so I could generate some guesses. Is the hypotenuse A plus B? And I could check it. I can check it with a ruler, right? So there's A, and if I roll that up and I add B, I don't have a good ruler, but you know how it's going to turn out. So you can check it pretty easily. There's A, and there's B, and my hypotenuse is right here, which is not equal to a plus b, so we know that it's going to be, at least in this case, less than a plus b. So I can rule that guy out, right? Maybe my next guess, it can't be a squared plus b squared, but I might try the square root of a squared plus b squared. And the reason I said it couldn't be a squared plus b squared is because that would be longer than a plus b. And you can kind of see that if I didn't know anything, I could just keep trying different patterns until I'd be like, hey, that one looks like it's right. I'm sure that wasn't how that one was solved. But so these are all different things. If you read kind of these strategies, and I highly recommend, read the book. It's from 1945. It's got some strange terms in it, but you should be able to work them out. I highly recommend it. I have a copy in my office, stained with orange juice and coffee. But the third step, after you have kind of come up with a plan, and you haven't solved it yet. You haven't solved it yet. So it's not really solved, but you convinced yourself you could. In math, you might have a proof idea. And if you ever read in your book, very often, instead of explaining a detailed proof, they'll give you this, the proof idea. And that's kind of your plan. The next step, step 3, is going to be carry it out. Carry out the plan. So the idea of carrying out the plan for us, so for step 3, I'm gonna write here, I'm gonna write it out as implement. And there's different ways that you could do it. Here, in step 2, you might have perhaps some pseudocode, which we're familiar with from the previous chapter, although I would argue that might even be down to step 3. Or a flow chart kind of idea, kind of a diagrammatic version of this going on. And here you might kind of turn this into actual code. All right, so carry it out, so check each step, right, in detail. If it's in pseudocode and you want to, you could trace the execution, trace the code, trace the pseudocode. If you want to, you could implement all or in part in the language of your choice, because we're talking about computer science here. You could implement it in Python, MATLAB, whatever, C++, and I would submit to you that this guy also loops back in on itself. You might want to do the thing that's fastest to check. And the reason is you don't necessarily know that it's going to be right. And you might encounter an issue like maybe rounding errors happen, and you didn't anticipate that 0.1 plus 0.2 does not equal 0.3, because in pseudocode that works, but in real code sometimes that equals something with a very small error. And if you haven't seen that yet, you might find that it's true when you go to implement something and you can't figure out why it's not working, which might cause you to go back and change your implementation in some way, and it might cause you to go all the way back. That might take you back to readjusting your plan, or even revising your understanding of the problem, because if it actually has to be implemented on a real physical computer, we have things like finite memory and finite precision, which are sources of errors, and they limit what we can do. So finite memory and finite precision, for instance, might show up here, limitations of your language, but pretty much this is probably straightforward. You know, if you did come up with pseudocode before, you can keep drilling down until you actually have code in some language. I could say assembly if you wanted to go that far, but that's pretty painful, as you've seen. And then the fourth step of Polya's method is extremely important. I'm just going to put here, do not skip, because everybody wants to skip this step. Because we're lazy, and it's the same thing as like dieting, and then you want to eat junk food. Everything up here, this is junk food. Generally, you know, you feel this rush of excitement when you're doing it, and then you see here, you know, it works once, and you're all happy, and you're having a party, and you feel good, and then this fourth step is looking back. Because you go to sleep, and then the next day you look back at it and you realize, wait, what did I do? Because unfortunately, very often an artifact of this process is messiness. It's sloppy and it's unclear. You cannot remember why you did what you did, and you won't remember it tomorrow. So for this, you want to look back at what you've done, and you want to do a couple of things. You want to learn from it. You want to simplify. Could I have done it? Could I have done it in a better way? Or a more general? And when I say learn from it and simplify, simplifying helps fix some of that issues, because you need to be able to use it later. And also, you learn from it. So learn from it, I can actually solve new problems better, because I learned something from this problem. So this is incredibly important, not just for engineering reasons. That's the way I write engineering reasons, but also for learning, which is what you're always doing, is computing. You do in your lifetime, hopefully, of your career, you will spend this much time learning in college and this much time learning in industry. And if this represents what you learn in college, this might represent what's actually relevant in your career. We try to get that to overlap, but unfortunately we're chasing a moving target. This is what's important now, and this is what will be important after 30 years. So it's just a fact of life that you're going to have to keep learning. So don't skip that last step. What you want to do, just reviewing here, understand the problem, very important. Understanding what's known, what's unknown. Ask a lot of questions. Ask questions. But also ask smart questions. You know what I mean? Use so there's a trap of just not thinking. You got to think first and then ask. I work with a lot of people who ask questions that they could have answered for themselves, and then at the end, there's something important that they don't know because they used up all of their time asking questions they could have solved on their own. So, analyze, if you're looking at this from a computer science point of view, your book kind of breaks it up a little bit differently. So your book says, from a computer science point of view, we might think of this, that first step of POLYA as analyze and analysis. Is that a Z? I don't know. And then they call that second step called algorithm development. And then that next step, implementation. And then that last step they're going to call maintenance. And I have a little bit of a problem with that because it focuses on the use of it rather than your personal learning experience. But overall, it's true. So you come along, you got some new problem, you analyze it, and you think it through, and then maybe you keep reanalyzing until you think you understand it. Then you go in and you try to develop an algorithm. And then that causes you to rethink the problem. So you go back and analyze it some more. And again, you keep adjusting your algorithm until finally it's time to implement it. And then, lo and behold, you discover there's new issues, and I need to rethink my algorithm, or maybe I need to go all the way back and rethink how I analyzed the problem. And then once I think I've got an implementation, we go into this maintenance phase. And in maintenance phase, you keep simplifying, and using it. And at this point in time, if you feel like you need to change the problem, you can start the whole process again. So this is sort of a software engineering type of lifestyle that correlates to POLYA's approach. So this kind of process is really important, and I'm going to stop here, but I want to wrap up with the idea that problem solving it's a skill that requires practice. There is a process that can help you, but it involves guessing. And the important word is intelligently. And it also involves wisdom, experience. And the idea here is you don't get to be able to ride a bike. What does a bike look like? Something like this, pedals. You didn't get to be able to ride a bike. There's my wonderful bike. You didn't get to be able to ride a bike by reading or attending a lecture. Although somebody explained it and you might have looked at something, you only really learned to ride a bike by doing it and by falling down. So I can't emphasize enough, for problem solving, you need practice. And there's another analogy I'd like to apply here as well that goes with this, and that has to do with, you know, when you go to the gym, you do not lift this thing up and down. You don't lift it up and down because my goal is to lift a weight. That is not really your goal. This is actually practice. and your goal is to get strong. Lifting a weight up and down is useless, except it makes you get stronger. I can draw better than that, muscles, right? And that, of course, might help you to lift a car up off of some helpless lady or gentleman in a skirt. I don't know. So, there we go, my wonderful analogy here. What you should get out of this also is we will try to keep things as relevant as we can in your in this course, but you should always be trying to find connections yourself. And there's a whole connectionist theory of learning, which is really important, and it's through here that learning happens. I can't give them to you. I can't lift it for you. You have to find your own connections. All right.